Hello, everyone. I am Marc Ballouz, and guess what? We are starting today the second International Interactive Technical Talk, or ITT, and this time it's about energy geotechnics with the Technical Committee 308. And this session, the TC308, because it is a wide open subject, we decided to divide it in two technical lectures. This time is a very important subject that I know nothing about, which is waste disposal of radioactive and nuclear waste. And we have our experts here with us tonight. I like to share my screen to welcome the three speakers. The representative of TC308 is the Vice Chair, Professor Alessio Ferrari, from the Institute of Technology in Lausanne, and he's an Editor-in-Chief of Geomechanics for Energy and the Environment. And then we have our young researcher from studying at Texas A&M University, which is a very famous and great university because I graduated from there. Welcome, Ali, author of My Fulbright and New Grade. I wish we had time for you to explain to us this book you wrote. And finally, creme de la creme, Dr. Maria Victoria Villar, researcher, and what struck me is characterization and assessment of behavior of host rocks and barrier materials for the disposal of radioactive waste. From all this paragraph, radioactive is a scary one, so I can't wait to hear what you're going to tell us, Maria. And welcome to this session. I will be the moderator. I will try my best not to speak a lot or interrupt a lot. And I like to start with you, Alessio. And I'm going to unshare my screen. And Alessio, the floor is yours.
Okay, now you should see my screen, right?
Yes.
Can you see? Good. First of all, Marc, I would like to thank you for this opportunity for our TC308 to introduce one of the more important, probably nowadays, topics that we are dealing with, which is what can we do with the disposal of nuclear waste. There is a huge, as we all know, discussion worldwide on the use of nuclear energy, about its continuation, in many times its return. Several countries are reconsidering to use nuclear power plants to produce energy. And as you know, one of the main concerns about the use of nuclear energy is what we do with the wastes, right? Fortunately, when we talk about nuclear wastes, not all the wastes have the same impact, I would say. Typically, most, you see here those bars, they give us a little bit the amount of waste which is produced around the world. Most of the waste are coming from the industrial and medical sector, and those waste have the advantage of having a relatively fast decay time. So it's the time when they will start to be dangerous for the humankind. And the highest, the waste with the highest risks are the one coming from the dismantling of the nuclear power plants, and especially those which are coming from the reactors. So the spent parts, where you see that the decay time start to be very, very long. We are talking about hundreds of thousands of years. And today our society, our geotechnical society, is asked to contribute to make provision and find solutions for a system that has to be effective for this duration. Okay, so we are really at the age of the scientific and technological challenges that our geotechnical society is facing nowadays. I don't know if you can see the entire screen, or you see.
I have a quick question.
Yeah.
10 to the power 0, 10 to the power 1, and then directly 10 to the power 5 for the medium.
Yeah.
And 10 to the power 5 to the high. It's like you're either low or high before you get rid of this securely decay time. Wow.
Sure.
Can you give us an example of 10 to the power 1 and 10 to the power 5, for example?
Yeah, typically what is coming from, for example, from medicine, right? You go, you get your raise when you have a broken leg or something. This type of waste, they will have short decay or fast decay time, so short time where they will be harmful.
10 years.
And they can be managed. They will manage it. For sure, they can be managed within a single generation, because what is really the result of these different numbers is that what we are designing today will impact the future humankind, right? The future of humankind. So this is why most of the research today is concentrated on this kind of waste.
Definitely, yeah. All right.
So now we will talk mainly about this high-level waste. So it's mainly the one coming. There was once coming from the nuclear plants, and this cartoon here is a kind of a representation of the volume that we have worldwide. Okay, and honestly, when you see those numbers and you think to the entire planet, I would say it doesn't seem so complicated, right? Because we are managing waste in many sectors which have much higher volumes, right, in terms of material to dispose. The issue here is that when we're talking about those high-level waste, they have a huge power to emit heat. So the temperature of the system that will be where they will be placed will tend to increase. And this is already an anticipation of the fact that the waste has to be confined, ensuring given distances between the packages, right? Because if we concentrate the waste too much, the temperature increase of the disposal system would be too high. Right? And of course, the other impact that we can imagine is about the radiation, right? So we want to distribute as much as possible the waste so that the radiation that will be emitted will be the lowest as possible in terms of concentration. What is the solution that it is foreseen today? And this is, I would say, accepted at the world level, is to create deep repositories. So what does it mean, deep repositories? Is that we are putting the waste down into the ground. And I'm showing you here the example of Europe, which is the one that I know better, but then Ali will complement also for other scenarios, that countries, many countries, they have already decided at least the type of geological formation where the waste will be confined. You see here that we have essentially two major solutions. One is to create this deep repository in clay formation. The other is to create the repository in crystalline rocks. For example, you see that countries like France, Switzerland, Belgium, Hungary, they are going for clays, while others like Sweden and Finland, they are going for rocks. And now I will show you what are the typical settings for those different types of disposal. And I have to stress from now that at least in Europe, there is not yet any of those repositories which has been built. There is one which is under construction nowadays, which is the one in Finland. Other countries, they are at different stages, or either of their selection of the site or the design of the repository, or they have already done some pilot disposal systems where they're testing their concepts. But let me show how will look like a repository of this kind. And this is the example of Sweden, that, as I said, they will build the repository in rock, in crystalline rock. So essentially it's a granite. And you see this huge series of tunnels at a very significant depth. Now we are talking about depths of several hundreds of meters. And within these tunnels, there will be the emplacement of those metallic canisters which are hosting the spent bar from the nuclear plants. Okay, so you see how the waste is spread in this huge layout. And as I say, this to minimize temperature increase and also radiation concentration. You see one key element, and this will be mainly discussed by Maria Vittoria later on, is what we put to fill the gap between the canister, so the metallic element containing the waste, and the surrounding material, is essentially bent. So we need the clay, a very active clay, to act as a barrier. And this is what we call the engineered barrier of the system. So it's the barrier where we can act with all our engineering tools. Another example is the one offered by Switzerland. So I'm putting here the Swiss case, an example where the disposal is done in clays. You see now that the layout has changed a little bit, and the emplacement of the canisters is done in a more horizontal layout. And this is typically done because clay formations, they tend to have lower depths or lower thickness, better said, so that you want to store the waste more in this horizontal way rather than in the vertical sense. Okay, so I can mention that the Swiss in a very special situation nowadays, because a few weeks ago the agency, which is the NAGRA, which is the agency in charge of the entire management of the nuclear waste, has announced the site where this repository will be built. And they have proposed, at least they are proposing the site at a depth of around 800 meters. Okay, so this entire set of galleries would be built and managed at a very significant depth. So why we want to go so deep in the ground? First, because you have to find a suitable clayey material, and those that have the highest chance to be effective, usually they are at great depths because they are quite old. This clay here is the famous Opalinus clay, has been sedimented around 180 millions of years ago, because it's a very old clay, extremely stable clay from a geological perspective. And also you want to have a significant depth because you have seen the duration of the system. We are talking about 100,000 years. We may also have to anticipate possible uplift of the entire system, for example, for erosion or glacial activities that can happen in these long durations. So you want to have the system at a given depth so that you have the highest chance that it will never come to the surface, okay, in those durations. Okay, I know that the other speakers, they will also integrate what I'm saying here. You see that there's a very general introduction at the moment, but let's talk about processes. So what can happen to the system from a physical or geophysical perspective, and especially from the mechanical point of view. So first, let's refer to the clay case, but this can be...
Alessio?
Yes?
I want quick question.
Sure. Mark.
Those what I want to call them nuclear trash cans.
Yeah.
They are, you showed example in Switzerland and one in Finland.
Yeah, Sweden, yeah, but similar thing.
Do they, and yeah, one is vertical, one
Yeah.
horizontal. And do they use this for their own waste, or some other countries can pay and dispose of their waste into these systems?
This is a very, very fundamental question. I should have mentioned this before, at least for Europe, but I think this now is extended worldwide. But I can comment for Europe. We have an Euratom regulation, which says that each country has to take the responsibility for the waste produced in the country. Okay, so a system like this, in principle, at least according to the regulation of these days, has to be built in each country.
But if a country is producing nuclear waste and is not ready to dispose of it, this is affecting the entire humanity.
It is.
Countries should help each other.
It is, and there are countries that nowadays they are hosting the waste produced by other countries as a temporary solution, but of course not for free, right? So the fees which are paid to the countries which are hosting the waste are huge. But for example,
sorry to interrupt. Please go, keep going.
Yeah, I can comment the case of Italy, right, which I know very well. So Italy has stopped its nuclear energy production at the end of the 80s after the Chernobyl accident. And there are still 5 nuclear plants which have to be dismantled. And the spent fuel from those plants is nowadays in England and in France. But it's a temporary solution. So at a given time, they
do you or Maria know if France is closing or expanding their nuclear power plants? Because most of the power in France is nuclear, right?
It is. It is. And even Italy banned electrical energy produced by the nuclear plants in France. So it is still.
And for them, I heard they consider this as the best and safest. I mean, they're expanding on renewables, but I wonder if they have a system or a program to close these nuclear power plants over time.
Not to my knowledge. I don't know if Maria, you have a different.
No, not that I know. I think that they are not planning to close because
and those power. Okay, they're not. And those nuclear power plants, do they produce waste that we have to worry about as geotechnical engineers and hide them under the ground?
So they are producing waste in the sense that I was commenting. So the spent fuel and also all the material which come close in contact with the reactor is also a nuclear waste that has to be disposed in the systems that we are describing now. In terms of policy,
so France should have many of those underground facilities.
All countries they try to concentrate in one big site. Okay, so France is very advanced in the program, so they have already identified the potential site where to build the repository, and they have a very large underground laboratory. We will see some examples later on for Switzerland, where they are doing experiments at the depth where the repository will be built. Okay, so there are a lot of demonstration experiments which are running to mimic as close as possible the real scenario when the real disposal will be closed.
And in the meantime, each
area?
Yeah, just I wanted to say, in the meantime, while we are waiting for the final site, each nuclear power station keeps their wastes on site in the pools that they have in the power stations. So that's
wow.
So they have to have some place to put this waste that is cooling in the pools before the pools are full. So,
wow. And do you have the same problem in Spain?
yes, it's everywhere. Everywhere is the same problem. The only thing is that in Spain, for some time, they have thought of putting all the waste in a superficial facility, not underground, but surface facility, like they do in the Netherlands, for example. But this would be a temporary solution. So, but at least they will keep all the waste in the same place.
Yeah, yeah. Keep going, Alessio. I hope
okay.
We can catch up on time.
Yeah. So we were just touching quickly the processes which as a repository of this kind will suffer, right? And in the case of clays, already we were talking about the depth of several hundred of meters, and typically those are formations which are saturated, and they have been saturated for millions or hundreds of millions of years. And now we are going to excavate tunnels. So we are, of course, changing the stress field, but also we are allowing the atmosphere to enter in the system, right? And we know clays, they will be exposed to air, they will tend to dry, and they could also be affected by damages, cracks induced by drying, and so on. Okay, so already there is this first issue of the stress distribution and this ventilation phase, which can desaturate and already alter the host rock formation. Then we say we put the waste, we put the barrier that we will be described better later on, and the barrier will be hydrated from the surrounding formation. Typically, those barriers are put into place in unsaturated conditions. So there will be Darcy flow from the formation to the barrier, and they will be hydrated. They will tend to expand because those are very active clays. And at the same time, the temperature field will be perturbed by the waste. So temperature will increase. So you will have these competing fronts. From a way you have the hydration coming from the host rock, from the in to the outside part, you have the thermal wave, which again tends to desaturate the barrier. Okay, so the system has to come to an equilibrium with these two processes which are competing. And you were mentioning, Marc, the metallic container which will host the waste. Even the best metal that we can produce today, it will suffer some corrosion effects when we think to these durations, right? And this, I know that Ali will touch this in his part. The corrosion of the canister will produce gas. And since we are in a very tight environment, so if you think to your ideal gas law, the volume of the space available is limited or constant. And if you have gas production, this will result in a pressure increase. Right? So the pressure of the gas can increase and can increase so dramatically that can even or could even break the barrier. Okay, so this is another big issue that nowadays the geotechnical and geomechanical community is facing. So how we can study gas migration in barriers, in clay barriers. I'm not sure that I will discuss everything I've prepared because since this is an interactive talk, I have much more slides than what I can present in 20 minutes. But just I want also to mention that we have seen the temporal scale of the complexity of the temporal scale of the processes. But there is also a huge complexity when we talk about the geometrical scale, right? because those materials, we're thinking here more to the barrier, to the engineering barrier, the response of those materials is very, very dependent to what is happening at the smallest scale, at the micro scale, right? And then we can move from the smallest scale to the real geometry, and we see that we are jumping for probably 10 orders of magnitude. So going to make prediction to this scale, which is the full scale behavior, requires that we are able also to understand what is happening at this micro or even nano scale. And my co-speakers, they will mention something about this. So we have understood that this is a very complex system. We have many variables which are interacting at the same time. So of course there is the mechanical part, stress, strains, response. We have discussed about unsaturation, saturation front, which is entering in the barrier. So there is a huge hydraulic component of the problem. There is also a temperature component, as we discussed. And there is also another variable that you see here, which is the chemistry. Because we are talking about very active materials when we deal with the barrier. And if in this very long duration, the chemistry of the pore water will change, because, for example, you can have invasions of different types of fluids in the barrier, we know that those materials, they will suffer also a change in their functioning due to the chemical part. So altogether, when we talk about nuclear waste, we often talk about the thermo, hydro, chemo, mechanical behavior. And this is wants to stress that all those variables are there, and that there are a lot of couplings between those processes. And here, I let you read, I will not discuss this in very detail, but you can also see that those variables, they are not just there, but they can have a huge variation. So let's see, for example, the temperature. You can easily go to temperatures of 100 degrees or even above, depending how you design your system. And there are not so many fields in geotechnical engineering where usually we are used to work with temperatures which are so high. Okay, this just to mention that fortunately we have the ability to deal with those complex systems. Okay, there are now, at least from the analytical numerical part, we have equations that can describe those complex systems. Of course, they are much more complicated than what we used to have in the current geotechnical practice. Most of the cases, we could just use the solid balance and the liquid water balance to solve a common engineering process. Here you see, for example, that we need to have also the vapor flux, which is described in our equations because temperatures are high. So migration of water in the vapor form has a role. We have also air because the system is unsaturated. So also air is flowing. We have also dissolved air, which is moving with the water. And of course, we have also the energy balance. So now you will see that in most of the talks that refer to our TC308, they always include some energy balance because temperature, when we talk about energy, is always a fundamental variable. Okay. So just the last slide is to give a little bit what is our mission in the sense of geotechnical engineers. So where are we contributing in this entire story? Because as you can imagine, there are so many actors and stakeholders involved. So here I really try to have a very short list on where we are contributing nowadays in this field. So geotechnical engineers are very active nowadays working for the selection of the appropriate host formations. So in many countries where there is still investigation on what is the right geological formation where to build the site. So once you have identified the geological formation, you also have to say the specific site where you will build the repository and also the right depth at which this will happen. Of course, there is huge work going on or that has to be initiated from the countries where this has not been started yet, is about the geotechnical characterization of all the materials and especially taking into account their heterogeneity. There is also a lot of work which is being done on the conceiving, manufacturing, and analyzing prototypes at different scales. So as I mentioned at the beginning, there is not a single site where a real bar, a real nuclear waste has been placed. Usually we build prototypes and we use heaters, so energy emitters, just to mimic what will be the impact of the nuclear waste. And we do this at different scales, from a laboratory scale up to the real field scale. Of course, we want to make provisions on a system that will last 10, 100,000, 100,000 years. The only way that we can do this type of forecast is with modeling. So nuclear waste disposal is probably the field which has contributed the most in developing thermo-hydro chemomechanical constitutive models, ability to solve boundary value problems, and so on. And those models, together with the monitoring of the active experiments, they are really the key nowadays to give us the confidence to make predictions of those systems at the various temporal scale, from the construction to the very end and long time duration that we have seen. I will just conclude quickly just to say types of experiments that we are been doing. I will just mention a couple of them.
Alessio?
Yes.
Sorry to interrupt.
Sure.
Can you go back to that slide? Because it's a very important slide.
Yeah.
Which basically summarizes our role as geotechnical engineers when dealing with nuclear waste. One quick question. Is it more important to have this impervious factor or the strength factor? In other words, is it better to select rock formation that is impervious, clayey shale, or you want to be in hard rock basalt? Which one do you prefer?
First, it's very country specific. Okay, it's very country specific. And then is also, it's more, I would say, a decision of the stakeholder, because the two different settings, they have two different views and which system is as the strongest barrier. Let me say in a different way. The countries that are going to use rock, like granite, they are aware that if in these geological times fractures are produced, they will not seal. Okay, so they will stay open. And this is why those countries, they are like trusting as the main barrier, the bentonite, so the engineering barrier which is placed around the canister. The countries which are using clays, they are selecting clays which have very low permeability, but typically those clays, they have also a quite significant swelling potential. So it means that even if some discontinuity will appear, like for tectonic processes in the very long term, the clay will have the ability to self-heal or self-seal due to swelling, right? So for those countries, the main barrier is the clay formation, and they can use still the bentonite as an important part of the system, but they are trusting more the clay formation rather than the engineering barrier. You see, it's more a kind of technical decision. The knowledge that we have today says that both systems can work, and then it's really a decision.
Nice. I like to hear Ali's opinion, and I see him shaking. He wants to say something. And Maria, of course. Quickly, which one do you prefer?
As explained by Alessio, I was just listening. So it depends on the country, and I think the technology they have, because the harder the rock is, it is going to be more and more difficult to build those tunnels and drill to such deep depths. And then again, if we are using, for example, soft rocks like shale, so the technical capability of using clay material as the main barrier should be there. So yeah, both can work depending on the country and the site. And there is one more.
Yeah, go ahead.
There's one more concept which I'm going to talk in my presentation in the US as well.
Okay.
Okay. Yeah, that is, as Ali says, depends on the countries, because there are countries that only have a crystalline rock, like the northern countries in Europe, Sweden and Finland. They only have crystalline rock, so they have no choice. And then there is Switzerland, for example, who have the two and have finally go for the clay stone. And I think the safety of this kind of repository depends on the system of barriers. It's not just one barrier. So we have the whole rock, but we also have the backfill and the sealing materials, the buffer, and so each part has a role, and the combination, what works is the combination of all of them. So I do not have any preference. In Spain, it's the same case. We have crystalline and clay whole rock, and we have not made a decision.
I got an idea, yes. So should I say, from what I understand, that if it's a hard rock, we don't worry too much about we increase the sealing material around it, make it a thick clay around the canister?
That might be a solution, of course, because this clay around the waste container, the buffer, has a high retention capacity, so it will tend to retain the radionuclides in its structure, which is something that the whole rock, the crystalline whole rock, will not do so easily.
So when you say it depends on the country, it's mainly what this country has in terms of layers, not politicians.
Yeah.
Okay. Next.
Yeah, just very quickly to conclude this part. Just wanted to show that there are experiments which have been already conducted for long durations. This is one done in granite in Switzerland. Maria mentioned that Switzerland had both options, the clay and the granite. So we have in Switzerland, we have two underground research laboratories. One is excavated in granite, and this is probably the longest experiment which has been conducted, is the FEVEX Benton. It lasted more than 20 years. So 20 years of observations, a partial dismantling to see the status of the barrier, and then the final dismantling that happened in 2015. Maria is one of the key figures in collecting and analyzing the data of the second dismantling. And very, very quickly, I just want to mention that there are modeling exercises which have been done and are still running to see, really, to test how our prediction tools, they can really be used to make predictions of those systems. So this is a little bit of self-advertisement. This is our attempt to model the FEVEX experiment without going too much in details. You see that somehow the numerical tools, they are able to reproduce the temperature field, relative humidity field, because hydration of the barrier is happening, and probably most importantly is also the density of the barrier as the hydration and the heating front, they have come to an equilibrium. The last example that I will quickly show is still in Switzerland, is the so-called FE experiment. This time the experiment is happening in clay, isoparinous clay. So this is, you see, the extension of the laboratory which exists in Switzerland, excavated in the clay formation. And in this laboratory, so one tunnel mimicking the final geometries of the disposal setting has been created. You see here, this is a metallic container, which is not holding the waste, of course, but is just holding heaters to simulate the wave, the thermal wave propagation. And also here, there are modeling activities that can make us to anticipate what is the response of the systems, for example, in terms of density evolution and saturation evolution of the entire system. Okay, so this is what
this is very advanced, Alessio. Wow, we need a much longer session.
Thank you very much.
This
Marc.
is very nice.
This is what I have prepared.
This FE is in Switzerland, right?
Yes, this is in Switzerland. But similar experiments are happening.
It's like 500 meters below ground.
The laboratory is around 300 meters.
300.
Yeah, this laboratory here is called the Monterrey laboratory. It's very, very close to France. Yeah, you see, it has initiated already in the 90s. So there are really several decades now of experiments which are
different colors or different years expanding.
When the laboratory has expanded. But similar laboratories, as I was mentioning, exist also in other countries. Okay, so France has one, Belgium has one. Okay, so this is all what I prepared for my part.
Thank you so much.
You're very welcome. And should we give the floor to Ali?
Ali, yes. Ali, you have to be faster than Alessio, unfortunately.
Yeah, I will try. Thank you very much, Alessio.
Thank you.
It was very elaborate and detailed. I will try to develop on the geotechnical part of it, like as geotechnical engineers, our role. So most importantly, it starts with site selection, which most of the time has been quite troublesome in a lot of countries, especially in the United States, where I'm right now, because it is considered that no state wants to be a dumping ground for the nuclear waste. And the criteria, as Alessio has already mentioned, the rocks should be strong, should not be very permeable, and then the site investigation is carried on based on where the site is selected, and the civil engineering design and construction criteria also consider the excavation disturbed zone. I'm going to talk in detail about it in my further coming slides. The type of rocks, this has already been talked about, but majorly we got crystalline rocks in some countries, argillaceous rocks, and the rock salts. So again, our preference is that the permeability should be low. It should not allow high ingress of water into the clay barriers, and it should have mechanical stability at the same time. So these are the two major parameters, and then of course the economic viability. We have the disposal boreholes. They are in the engineered barrier system. They can be vertical and they can be horizontal. Both have their pros and cons. I'm not going into detail of each of it, but it is easier to drill vertical boreholes, but then there can be accumulation of water as well, and it can result in the swelling of the clay barrier sometimes. This is a schematic diagram of the engineered barrier system. So as you can see, we have the tunnels, and the tunnel is providing the host rock. I can have this pointer. So we have the host rock, and then in the center we have the canister, which is holding a steel container, which is holding the vitrified or processed high-level waste, and the gap between is filled by clay material. So there are two proposed ways in which this clay material can be used. One is the blocks of compacted bentonite. So so this is an example where these blocks are put in place, and in the actual repository, so there's a plan of using robots for doing that. And the other proposed way is to use small pallets. So these are the pallets, for example, these are rounded shape. They are 7 millimeter. The one I have been working on during my research. So it is, the placement is much easier compared to these blocks, and we can use this auger system. So we don't have to use a very sophisticated and mechanized way. So
Ali, I'm gonna interrupt you.
Sure.
With a question, just because. So when you place, let's say with the auger system, do you spray water behind you so it expands and seals, or how do you count on sealing it? Like dry and compacted blocks is not sealing. So
so as mentioned previously, the design life is hundreds of thousands of years. So we expect that ultimately the groundwater is going to infiltrate and it is going to interact with these swelling clay bentonite pellets, and then that will cause this pellet to swell and completely seal all the cracks and all the openings, and that will result into a very tight system.
So we don't spray water, we count on the ground to seal itself.
Yeah.
I don't want to be there first few years.
The hydration part is majorly, the thing is that the stainless steel, and because it is buried very deep, so we are not very afraid of leakage or radiation coming out in the initial years. But as with the passage of time, I'm going to talk about that the changes which we expect due to the corrosion of the steel. So then I think the role of the clay barrier becomes even more important. It is always important, but that is the time when we are a lot more relying on it. This is just my opinion. I hope I can answer your question.
It's good, keep going.
And then I'm going to talk about what's happening in the USA. So in the 1970s, certain, I think 10 sites were selected for the disposal of nuclear waste, high-level nuclear waste material. And after 2 or 3 years, the Yucca Mountain was the only man standing. And then this site was selected. The concept here is different from what the Europe has been doing, because the Europe concept is multi-barrier system, which consists of several layers of barriers trying to hold the high-level waste. Like it's a stainless steel container, then it's the clay barrier, then it's the host rock. But here we do not have any engineered barrier system. So it relied majorly on developing tunnels and storing the radioactive waste. And because, as Alessio mentioned, it generates heat. So all the water which would be entering will be evaporated, as you can see here. But this project was suspended in 2011. So again, because of the technical and political reasons. So right now, it is in a limbo. Coming to the situation, there are over 85,000 metric tons of spent fuel in the United States. So I think this is approximately one fourth of what the entire world has. And the Department of Energy in America is responsible for the safe disposal and the permanent disposal. Every year, we are having 2,000 metric tons of additional nuclear waste material. So one thing I would like to mention is the capacity for which this Yucca Mountain was proposed. The amount of nuclear waste that is already present in the US is more than the proposed capacity of the Yucca Mountain. So even if we start storing the nuclear waste today, we are going to need an additional site or an expansion of this already proposed project. The Blue Ribbon Commission that was working on that on this project proposed that in order the construction of a repository to be successful, we have to have the solution have to be flexible and adaptive in a way that we have to consider the technical, social, and political development all along the way. And it should be a staged process. It should be consent-based. All the stakeholders should be taken on board. The process of selection of the site has to be transparent and technically very sound. A little about Pakistan, the country where I belong. So we have 6 nuclear reactors, and one of them is under repair. So we are generating 3,200 megawatts of electricity. So it means that in very near future, we are also going to need this this facility where we can permanently and safely store the nuclear waste. Since Pakistan is not the member of nuclear non-proliferation treaty, so this hinders a little bit in the development of the civil nuclear energy projects, but China is very helpful in this regard, and International Atomic Energy Agency is also supporting the civil nuclear program in Pakistan. As I mentioned about the excavation disturbed zone before, so basically this is the zone which is strongly affected by the drilling process, leaving additional cracks in the rock. So these additional cracks means more pathways for the gas, which is produced. So the gas is basically, the hydrogen gas is produced when the water from the host rock that infiltrates through the host rock and interacts with the clay barrier, and then crosses the clay barrier and reaches to the stainless steel canister. So that is the point where the steel interacts with the water and the corrosion starts. That results in the generation of the gases. The gases have no way to, because as I mentioned, that when the water interacts with the clay barrier, it swells, blocking all the cracks and all the openings. So the gas which is generated cannot go out in a sealed system. So the pressure keeps on rising. And based on some numerical simulation, we have a prediction that, for example, over 50,000 years, after 50,000 years, this pressure can be as high as 1600 megapascal. So it is, so these so this high pressure can result in the escape of the gases, and supposedly one of the potential pathways is the interface between different material, the interface between the host rock and the clay, because these are two different materials, and at the interface there is high possibility for the escape of the gases. A lot of researchers have studied and investigated this possibility of the gas escaping, including Dr. Sanchez, with whom I have been working in the lab. So a little more of what we have been doing about this gas. So we also wanted to study this phenomena of gas migration and gas breakthrough through the interface. So we developed this prototype in the lab. So you can see that this is a host rock. So in our research, we use argillite rock. And then in the center, this is the clay material. So this is the interface between, this is the rock and clay interface, where we are interested to see the migration of the gas or the breakthrough of the gas. So breakthrough of the gas is, in simple words, is just the migration of the gas when your clay barrier is fully saturated. So we developed this thermohydromechanical cell in collaboration with the UPC Barcelona, and so this clay barrier prototype, engineered barrier system prototype consisting of host rock and the clay was sandwiched between the pedestal and the piston, and the attempt was to mimic the field conditions. So once it was placed, the confining stress and the vertical stress was applied, because in the field the engineered prototype system is going to be under stress. And then, as I mentioned, that after thousands of years, the groundwater is going to interact with the rock and with the clay material. So in order to replicate that, we started hydration with the help of pressure volume controller from the top and the bottom. This caused the clay material to expand and become fully saturated, which means that now the bond, rock and clay bond is the strongest. Interface bond is the strongest. And then to check the, to replicate the field condition of production of the gas, we used another pressure volume controller, and we started injecting gas into this system at a constant flow rate.
Yeah. You're using nitrogen as a gas?
Yeah, we are using nitrogen because it's inert, it's not hazardous and not flammable. So this is also, as you can see, this is also a tight system. So the gas has nowhere to go. So the pressure of the gas is rising. Gas is being accumulated at the upstream of this sample, engineered barrier prototype, and the gas is being accumulated and it's increasing and increasing. The pressure is increasing until there comes a time that this interface can no longer hold the gas pressure, and the gas break through this interface and is recorded with the help of the gas flow meter. So this is the argillite host rock that we got, and then we are also looking at the effect of the interface of the roughness of the interface. That if the rock and clay interface is not smooth, how it is going to affect the breakthrough pressure and the performance of the engineered barrier system. So these are some of the results that we have obtained. We are also in our group, we are doing numerical simulation to further understand the concept of the gas breakthrough and to project it to larger scale and different scenarios. So that's all from my side. Please let me know if you have any questions.
Thank you, Ali, for your presentation.
You're
Maria,
very welcome.
I can't wait to hear your experience.
Okay, I try to be fast. Yeah, the other colleagues have already presented many aspects of what I'm going to say again, but I'm going to focus on the material characterization. As it has already been mentioned, the security of this repository concept, the underground, geological underground repository, relies on the use of a series of combined barriers, the multi-barrier
I'm sorry
concept.
to interrupt you. Are you guys able to see the slides?
I thought I had. You cannot see them?
No.
Sorry. No, I haven't. Okay,
yeah.
Now. So
Thank
as I
you.
was saying, and has already been mentioned, we have the host rock and even the biosphere as the natural barrier, and then we have this system of galleries, shafts, and tunnels excavated in the host rock that have to be backfilled when the repository is closed, so they cannot be left open, and we have to put the backfill in them. This is put to support the rock and limit the expansion of the buffer. The buffer is the material that is in direct contact with the canister. So here you have two different concepts, vertical and horizontal, and these transport tunnels and deposition tunnels would be filled with the backfill, and then around the containers, the buffer or the sealing material will be placed. And then we still have the overpack or the container, and even the form in which the waste is emplaced, which is vitrified, is very inert form, so it's another kind of barrier. This buffer that will be in contact with the canister and the host rock, its function is mainly limit the entry of water and contribute to the radionuclide retention and the heat dissipation. So it should also provide mechanical protection for the canisters. As Ali explained, and the material normally used is bentonite, which is a clay rock. It's composed mainly of esmetite, which is a kind of mineral that is expansive and can retain elements in its structure. That's why we expect that it will contribute to the retention of the radionuclides once the barrier of the canister is broken or deteriorated. It can also be used mixed with other aggregates, other kinds of materials like crushed granite or quartz or zeolites, graphite. This is done to improve some of the properties and also maybe to reduce costs. And this has also been explained by Ali. It can be prepared in the form of compacted blocks or like pellets that can be mixed with powder. Or we can have a combination of all these materials in the same barrier, like in the Swiss concept, where they have the canister resting on a pedestal of compacted blocks, and then the rest of the gallery is surrounded by pellets.
Sorry, Maria, to interrupt, but from what you're explaining, I feel that there is no code. So it's like this these techniques are still based on the innovation of each site engineer or project. So it's not like an systematic code like in concrete construction, for example. Or,
no, there is not
so
a
we are still
systematic
at a
code.
very early stage. And I want to go back even to what Ali was saying with the USA stopping the program in Yukon Mountain, and that we are not ready in Europe. It's a bit scary that each nuclear facility is taking care of its own waste. Is this correct?
No, but there is also a lot of research that is performed in framework of international projects. So there are a lot of common patterns. For example, well, the depth at which the repository has to be excavated, the kind of materials, the properties that the bentonite should have, densities that should be used, what should the permeability, the swelling capacity be, the factors that affect them. All this is quite well studied and known. But then the technical details, probably there are other people working on those, but it's less developed because not many countries have already decided on a site and a concept. As Alessio explained, there is one of the repositories, the first one that is being constructed in Finland, and also France and Switzerland are also quite advanced. But the rest of the countries are delaying to make a final decision, because this has also a lot of political and social implications. So it's not it does not only depend on technique and science, it depends on other factors that escape us. So well, also of course money, but yeah. There are many aspects that are well known and that we all agree in. Probably the main ones, although there are still details to fix. So well, as also Alessio started explain a bit, there are a series of processes that take place in the bar. I'm going to focus on this buffer material, the one which is in contact with the container, with the waste container, and once it is placed, immediately it will start to be hydrated by the groundwater coming from the host rock. So once it is hydrated, it will swell, it will fill the voids, it will seal, it will develop this high swelling pressure. The air in the pores will be compressed and there will be chemical changes. And then at the same time, we will have the waste heating the environment because of the radioactive decay of the waste. If the temperature is high, Alessio already explained. So there will be desiccation in the barrier close to the container, shrinkage, maybe cracking, vapor convection and advection, and of course there will be chemical and mineral changes and this gas generation and transport that Ali explained. So here, for example, we have here, these are actual measurements in an in situ test in Monterrey in Switzerland, where we have the temperature as a function of the distance to the gallery axis, so as if we were from here to the host rock. And we can see that in the part which is the buffer, the engineered barrier system, we have a decrease of temperature from 140 at the contact with the container to 30 in some cases. So it is a huge thermal grading that we have, and it will remain for many years. This is just a prediction until 20 years. So with all these processes, we can. Yeah.
Can you go back? Quick question. If I look to the top left cross section, I see the canister, and then the buffer, which is diameter 5 times maybe of the canister, and then the host rock. Are these canisters standardized? Is there one manufacturer worldwide, or is it random? Who makes these? Is it like a propane bottle that
no,
same manufacturer distributes, or just to explain to the audience? And then how big is it? And the buffer, is it also a standard diameter beyond it, or depends on the designer?
No, this cartoon first, this is not at a scale, or it's at the scale of a particular experiment, but the buffer may have less thickness than this. This is also dependent on the repository concept of each country and on the buffer that they use, because there are different kinds of bentonites. Some of them are more pure or have different, well, exchangeable cations, so their properties may vary. So depending on the properties, the thickness may change. So this has to be decided once the site has been selected. And with regards to the canisters, for example, I know in Spain they are all standard, and I think it is an American design, so maybe in America there are similar ones, but and they are carbon steel canisters. But for example, in Sweden they are copper canisters. So this is they are not the same in all the countries. They maybe some countries have the same, but not necessarily. So yeah,
I see in the graph. I see in the graph that the EBS is like half a meter. It's pretty effective in reducing the heat.
Mm-hmm. Yeah, it's not a particularly well heat conductor, the bentonite. It's okay, but not particularly good, especially if it is dry. And that's why in some concepts that they have considered to mix it with quartz or even graphite, because those materials have much higher thermal conductivity, so the heat dissipation could improve.
I'm guessing that during the experiment, these bentonite blocks were saturated, right?
They should be eventually, in most cases, they would be saturated.
Yeah, during the experiment, was the water controlled, like to maintain some sort of saturation, or?
Normally, when these experiments are performed in natural laboratories, as Alessio explained, hydration is left natural, so there is no forced hydration or anything. So it's just the groundwater coming into the barrier. Some cases they inject also water, but this normally not in these experiments that are carried out in underground laboratories, because what we want is to simulate the conditions of the actual repository. So we don't want to introduce factors that are not going to be there. So the characterization of these materials that are used as buffer or backfill, comes from in their particular properties. They have a very low permeability and a huge swelling capacity. Besides, they are used compacted, and this enhances these properties. So when we started to test these materials in the laboratory, like 30, 40 years ago, new equipment had to be designed. Also, because of these thermal gradient that we have seen that we may have, and the high temperatures, the buffer will remain unsaturated for a long period of time, especially if the groundwater availability is not high. So when these materials started to be studied at the end of the 80s or beginning of the 90s, the unsaturated soil mechanics was very much developed, both from the experimental point of view and the modeling aspects also. And for example, there are some codes that were developed in the context of these areas, such as the Barcelona basic model, which is very well-known and used code for unsaturated soils. It was developed in the framework of reactive waste disposal. Also, this, as I said, we have been saying, this buffer material can be subjected to high temperature, gas can be generated and transported, and we can use the material prepared in different ways. So all these pose challenges for the lab experimentation, and we had to consider new aspects that had not been considered before in experiments or model. These have already been discussed in the previous talk. So some examples of what I mean with these challenges and new developments. We faced the testing of materials that have a very low permeability. So the flows that we are going to measure when we try to determine the permeability are going to be very low. So we have to use equipment which is advanced to be able to measure such low flows. For example, these pressure volume controllers. Also, normally we cannot use triaxial cells because we cannot restrain the swelling with them. So we have to use cells, stainless steel cells, where the material is confined and cannot deform, swell. And the hydraulic gradients that we have to apply are higher than normal ones, because otherwise we may not have flow. So when we have to keep in mind that we are trying to measure hydraulic conductivities that are in the order of 10 to the minus 12 or 13 meters per second, which is really low. The same for swelling pressure. The swelling pressure is so high, we are talking of some megapascals, that at the beginning, when the laboratories started to work with these materials, they had to modify their odometers, either making very, very long lever arms, or reducing the size of the samples, or then eventually they develop cells like this one, in which the load cell is built in the cell. So it's a stainless steel cell, well confined, and we measure pressure with this load cell as the sample saturates. So this is interesting because we have the evolution of swelling pressure over time until we reach equilibrium. These normally are very long tests, and as you can see, the swelling pressure, here we have the main parameter that affects swelling pressure is dry density. So here you can see that we are talking of swelling pressures of several megapascals, huge ones. These are not normally considered in a normal soil mechanics laboratory. Another aspect that was quite innovative is the development of material of equipment to test the material in unsaturated state and controlling the suction of the material. So odometers, to work with suction control. Even triaxial cells were developed with different methods to control the suction. And then an aspect that has been very much developed is the determination of the water retention curve in expansive materials. This parameter, the water retention curve, is very important to predict the time at which the barrier will be saturated, eventually saturated. It is as important as permeability. So we have now a very good knowledge of this water retention curve for bentonites, for expansive material, which factors affect them, density, temperature. Here we have examples of how the water retention curve is affected by temperature, or even the salinity of the water. And then we have to study properties that normally are not considered in geotechnical investigations, such as the thermal properties. Alessio also mentioned the thermal conductivity that has to be determined to predict the thermal field in the repository, which is affected by mineralogy. It increases water content with dry density, so with the degree of saturation, and also with temperature. So developments were made to measure the thermal conductivity of these materials as a function of temperature, as we can see here. And then we had to test these properties at high temperature, not just at room temperature, because this is how the barrier is going to work. It's going to work under relatively high pressure. So new cells had to be developed. We have to use materials that have a low thermal expansion coefficient. To increase the temperature, we can use thermal mats around these cells or put them in ovens or in thermal baths. We have to take into account that the variables are going to be affected by temperature. So if we normally apply a back pressure or pore pressure of 6 bar, we have to consider that if we perform the test at 80 degrees or 100 degrees, we probably will have to increase this pore pressure to keep the water in the liquid state. If we want to measure variables like temperature, relative humidity, or stresses, we are going to have to use sensors that are able to withstand high temperature, so special sensors. We will have problems of vapor leaks that have to be controlled, and it is very important when we test at high temperature the good and accurate calibration of the laboratory equipment, because it is going to deform and develop stresses when we heat it. And we have to be able to tell apart the deformation of the equipment from that of the material that we are testing. And finally, this is my last slide. I just wanted to mention, since we are working with complex fields, thermal gradients, hydraulic gradients, there are coupling of processes, and these large-scale tests that Alessio presented are very interesting, but you can imagine they are very expensive to be mounted, and then they are running for many years. And if we want to get information in shorter time or under well-controlled conditions, what we do is we work in the laboratory in these what we call thermohydraulic cells. What we do is, at the scale of the laboratory, we try to simulate the same conditions that we have in the barrier when it is in operation. So we have cylindrical cells that have, for example, the length of the material is the same as the thickness of the barrier. In this case, the barrier was 50 centimeters. This is an in situ test. So the height of the cell is also 50 centimeters. We have a heater at the bottom, which is set at the same temperature as the surface of the container. In this case, it was 140. And then when we hydrate through the top with a water that it has the same chemical composition as the groundwater. We can, of course, we can instrument the cell with different sensors, temperature, relative humidity, stresses. So we have the evolution of these variables over time. This is very interesting for models because it's, the data can be used to validate the models. The material that we put inside the cell has the same characteristics as the material that is going to be in the barrier in terms of dry density or water content, or if it is a compacted block or pellets. And then when we dismantle these cells that can also be running for many years or for different periods of time, we obtain post-mortem information, which is also very interesting, and to check, for example, the swelling capacity or changes in mineralogy or other physical or physical-chemical aspects. And I think this is all I wanted to say. So thank you.
Very nice expression. Oh, thank you, thank you. Thank you all. I have one quick question, if you stop sharing. It's because my background is classical geotechnics. I learned so much today. Thank you very much, all of you. So it occurred to me, and that's why I was asking, if you noticed twice, if you hydrate that barrier, and this question is for all of you, but if you look at it in 3D and you're not doing controlled hydration, the canister is cylindrical, and vertical is like a pipe. So if water is coming to hydrate this buffer, it's hydrating it from one side. So there is a danger of crushing that canister because the high pressure swelling force that you showed us, Maria. Maybe I'm wrong. The hydration is not all around, so it's not compressed equally. And I wonder if somebody looked at this problem.
If I may comment on this.
No, but
so the hydration actually is coming in a kind of annular form, right?
Yeah.
Because the gradients, which is driving the flow, is essentially the result of the suction of the material. So the fact that the pore water pressure inside the barrier is extremely negative. So you will have a gradient from the surrounding rock where the gravity effect is marginal with respect to this initial suction. So the hydration will occur really in a kind of axial symmetric condition. But what you mentioned, Marc, is a very, very important aspect. If the canister can bend or not, right? Because probably if there are the dry density of the barrier is not homogeneous, and since the swelling pressure of the material is strictly linked to the dry density of the barrier, you may have some bending of the canister. This, for example, was one of the topics that was discussed in a very long European project, which was called Beacon. What is the role of the initial possible non-homogenization of the barrier on the repository system, on the behavior of the entire repository? So it seems that anyway, the barrier will tend to homogenize in a sufficient way so that the stress states on the canister will not be that deviatoric in a sense, then can have important bending on it.
So one of the things as geotech, I don't know if you can hear me.
Yeah, we can.
Yes, we can.
So we should add as geotech to the list of tasks we have to give is the structural engineer designing the canister, the earth pressure on that canister.
Sure.
Expected.
This is typically one of the outcome of our of this modeling exercises.
Okay, good.
There are also very innovative aspects related, for example, to the friction. what is the role of friction between the metal and the bentonite, right? So this is another very urgent topic which is discussed in this community. And also, since you're mentioning this kind of more structural issues, no one of us has mentioned the lining of the tunnels. So what is the best way to design lining, and hoping that this lining will last for probably hundreds of years, and at a given time is the barrier who has to support the tunnel, because even the best concrete or thing that we can plan today cannot last for 10,000 years. So we trust that the swelling pressure of the bentonite will sustain the tunnel. Those structural aspects are very, very important topics also in this field.
Yes. Alessio, Ali, and Maria. I like to conclude here, unfortunately, and don't be sad because it's impossible to cover all the aspects of the subject or any subject. The goal of IITT is to interact among each other as the geotech family from different parts of the world, young and renowned. And I think you did a great job enlightening, especially me, coming from classical geotechnics. I learned so much from you tonight or today. I don't know where you are. I am here in Indonesia today for opening their National Geotech Conference tomorrow. And I was very, very happy to take part of this talk. And thank you so much for giving your time and preparing those slides. I know it takes time, and I want to reward you somehow. And I want to tell all our audience, I hope you enjoyed it and learned some, at least some. I learned a lot, and we're gonna launch this very soon. And next will be another session of TC308, and so on and so on. The goal is to have technical talks every month, at least one, until we cover all the technical committees and the subjects of geotechnical engineering. Thank you very much.
Thank you, Marc.
Bye-bye.
Thank you all.
You can
Thank you.
Bye.